Thank you. Today I'll discuss some work that we had done called cite2vec on exploring document collections through word embedding. So this is a joint work with Catherine McDonough at Northeastern and Leeds University at AFRL. So the focus of our work is in exploring large and rich document collections. And so this is becoming an increasingly important and complex problem for a number of domains. So for instance, in scientific literature, it is essential for researchers to stay on top of the state of the art, even as the number of articles published increases each year. And so as an example, if you consider the fields of computer vision and machine learning and look at the prominent conferences, just this past year in 2015, there were a total of 1,800 papers published. So it's really critical to stay on top of that, and really hard when the number of papers published each year is just increasing by that amount. In journalism, similarly, there's a need to search and explore large amounts of news articles in order for journalists to craft their story. So there are several objectives that we'd like to achieve in document exploration. So first, we'd like to understand the general themes in documents. So for instance, in a corpus of computer vision papers, the types of themes we'd like to see emerge should be object recognition, segmentation, and reconstruction. So secondly, we'd also like the user to discover documents of interest. So this is something that the exploration should enable. And last, we'd like to have an effective means of comparing documents. So for instance, what makes certain documents similar, what makes them different, and why. Now, all of these tasks are largely driven by how a document is represented. And a very common representation of representing a document is the document term model, where if we take, for instance, this example text, a model will represent this text as a point in a high-dimensional space where each dimension represents a word from a predefined vocabulary, and its value reflects the frequency of that word. And so this type of model has been used extensively in the visualization community for exploring document collections. So for instance, Tiara uses this representation for visualizing documents via latent Dirichlet allocation, where topics are constructed as mixtures over words, and documents are represented as mixtures of topics. So similar works have used non-negative matrix factorization to represent topics, and an efficient means of manipulating the model. And this can be seen, for instance, in the recent works of Utopian and Topic Lens, which was presented at Visit this year. So these techniques visualize what a document is, and they do this through the set of words that comprise the document. But in some situations, we might want to explore how documents are used. And so as an example, consider some common usage in research articles. So people use research papers for a variety of reasons, such as it's actually like a survey, it's a component of a technique, a data set, a benchmark, some sort of evaluation methodology, some implementation, some piece of code. An effective means of exploring documents through how they're commonly used can enable researchers to discover documents for their own very specific use cases. And hence our main goal in this work is to visualize documents through their usage. Now, we note that usage may not be captured by a document's text. So document usage may evolve over time, different from how an author viewed the original document's intention, how they actually originally wrote it up. And so our main observation is that we can capture this notion of document usage through citations. As an example, if you consider this snippet of text, we can readily observe that the cited paper is being used for evaluation and just looking at its surrounding citation context. Similarly, you see that this paper is being used as a data set if you look at its surrounding context. For instance, in just the underlying words of Amazon, webcam, things like that. And last, we can observe that this paper is being used as part of the component of the approach. So we present cite2vec. So this is a technique for exploring documents through the context in which they're cited. And we use neural language models, and in particular word2vec, to jointly represent words and documents as an embedding in a high-dimensional space, such that citation context is preserved. The proximity of words and/or documents is reflective of their similarity in this space. Our strategy for visualization is to project documents and words from this embedding into a common 2D space. However, the complexity of the embeddings can easily lead to subpar projections. So to get around this, we take advantage of Word2vec's property that the embedding exhibits linear structure, where documents can be expressed as arbitrary sets of words or even other documents, as well as certain forms of analogies. And so as just the nominal illustration, if we consider this embedding of words and documents on the right, where purple icons represent words and green icons represent documents, if we consider the two words shown here, video and segmentation, then the addition of these words embeddings will represent the composition of the meanings residing close to documents that reflect video segmentation. And so what this enables is the user to dynamically steer 2D document projections based on their specific interests. So here we show our system in use. The user can zoom and pan the word cloud in order to obtain themes in the document collection and get ideas for exploration. We first show the projection of all the documents, where each document is positioned near relevant words, as well as other similar documents. By typing in an arbitrary phrase, each shown word changes its meaning to be composed with this phrase. So this results in two different operations. First, documents for which their nearest composed phrase is unrelated are filtered away. And secondly, the document's projections are updated to best reflect the phrase composition. The user can also input multiple phrases in order to compare documents based on different forms of usage. This enables the user to interactively modify projections to their interests and organize document projections around concepts that are relevant to them. So we first describe our general data processing. So given our document corpus, we treat it as one large stream of text. And so we note that we don't actually retain the identity of the documents. The documents that we're visualizing are those that are cited by the corpus, but not the corpus itself. So from a collection of PDFs, we first extract text and resolve citations. We extract text through a pretty standard PDF, the text parser, and we use the parsite software package to discover and resolve citations. So just a quick illustration, if we have these two snippets of text from two separate documents, we can analyze the reference information for these citations, and we observe that these refer to the same paper. And as a result, we can resolve these as belonging to a unique identifier. As a running example, and in our experiments, we use a computer vision corpus of papers, where this consists of around 12,000 papers, and it yields approximately 70,000 documents that are detected through this process. So our document representation goal is to find a high-dimensional embedding of documents in such a way that local citation context is preserved. And we achieve this through the skipgram model of Mikolov et al. So we first go over this approach for words. So if we consider a given word in the text W sub I with its associated vector representation, the model aims to maximize the log likelihood of the following, where in considering words in W sub I's neighborhood, denoted W sub I plus C, we would like to make their inner product as large as possible. And so to illustrate this, let's consider the following snippet of text. Suppose that the word we are on is embedded. We scan over all nearby words, and what we do is push their embeddings to be as close as possible. Now, satisfying this alone, however, can result in the trivial solution of each word having the same vector. To enforce discriminative embeddings, negative sampling is performed, where we consider words that are randomly sampled from a distribution and then push these away from the target word, where the distribution is taken to be the unicorn distribution over the corpus. We then perform this over all words in the corpus using stochastic gradient descent in order to scale to a really large document corpus. So in considering documents as citations, we can perform the same type of process in embedding them in the same space. So in revisiting the earlier pair of text snippets, we associate the citation as a unique point in the space, and its neighborhood is all nearby words and potentially other documents. We then push neighboring words and documents together while pushing randomly sampled ones away, giving us a joint embedding of words and documents in the same space that captures citation contexts. Now, an issue with this approach is the discrepancy in the document word distributions. So document citations tend to appear far less than words. But by performing negative sampling with respect to their individual distributions, we can resolve this bias in order to yield more effective embeddings. So first we'll show our word embeddings and how they relate to each other. So to do this, we just perform k-means, and for each cluster, we retain the words with highest frequency. So we can see that some clusters correspond to more traditional computer vision concepts. Others refer to matrix concepts, more generally measures. But interestingly, we also capture concepts related to, for instance, code and implementations As it's common for papers to cite other papers because they're using code. They're using the code that's backed by the paper. We also capture different categories of data sets. Here showing animals and scenes. And we also show a cluster here that represents theoretical concepts. And so what's nice about this is that these examples demonstrate that our word embeddings are effective in preserving semantics. And hence we can allow users to express arbitrary words for exploration and allow them to express it in the same type of manner that these documents are originally cited, and in particular their citation context. And so secondly, the embeddings exhibit a nice certain linear structure where the addition of the two word vectors represents the composition of their meaning. And so this follows from the objective, where if we consider a given word W sub I and its neighboring words, for frequently co-occurring triplets of words, we have the following, which states that the log likelihood of the addition of two word vectors is proportional to the addition of the individual log likelihoods, which is what we're optimizing over. Hence, our embeddings naturally satisfy word vector addition and hence word composition. And so a similar reasoning holds for document and word composition. And this important property enables a lot of flexibility in document exploration and how we perform word document projections, which is what we discuss next. So we first address how to sample words and project them to 2D. We'd like the words sampled to satisfy the following criteria. They should cover general themes in document usage. They should be semantically distinct from one another, and they should be multi-scale to allow for level of detail as the user zooms and pans the 2D embedding. So we achieve this in a two-step process. We first perform farthest point sampling of the document embeddings, and then select representative words. So we illustrate this below. First, we select the document at random, and then we select each subsequent document such that its minimum distance over the preceding documents is maximized. Words are then sampled that are in close proximity to these sampled documents. And so by doing it in this process, we ensure that any subset of words will be well spaced as well as relevant to the documents. So we then perform TS&E on the sampled words to obtain our 2D projection. And here we show an example projection with each word color mapped based on its appearance in the sampling sequence. Purple is early and green is later. Our projections preserve properties from the high dimensional space. Hence we can use the embedding to remove clutter and introduce words as the user zooms, rather than more traditional 2D level of detail word placement, in order to more faithfully represent the content of the embeddings. The projection serves the purpose of conveying the general themes found in document usage so that the user has an understanding of the types of concepts to explore. In addition, it grounds the document projections, which we discuss next. So we would like our 2D projections of documents to satisfy the embedding of the geometry as best as possible. And so to this end, we use the least squares projection approach of Pavlovich et al. To position the documents in 2D. So we form a graph Laplacian based on the embedding, and by setting it to 0, we enforce each document to be positioned such that it's the weighted average of its nearest neighbors, weighed by the similarity that's inherited from the embedding space. Now, unfortunately, this trivial solution is to assign each coordinate to the same point. So to address this, we'd also like each document's projection to satisfy the 2D word projections. So we use each document's nearest word in the original embedding space and use that word's corresponding 2D projection as a soft constraint in the Laplace solve, balancing both objectives to arrive at a projection. But we can do more than just this static projection, however, with the composition properties. We allow the user to steer document projections by modifying each document's nearest neighbor through different forms of interaction. So we allow the user to specify arbitrary phrases in order to better explore the document collection. In so doing, each word takes on the meaning of itself composed with that phrase. The document's positional constraints are then updated with the closest composition, and the projections are subsequently found through the Laplace solve. Additionally, we can specify documents as concepts for words to compose with, enabling the user to mix and match words and documents to refine their exploration. So here we show an example where, upon specifying a given phrase, each shown word's meaning takes on itself composed with that phrase, and each document either moves to a more relevant word-phrase composition or is filtered since its best composition poorly reflects the document. In practice, this results in documents moving to more detailed meanings. In this example, we see documents move to regions that are more specific uses of convolutional neural networks. And here we show an example of document composition. So documents can have a very rich representation in the embedding, leading to a very expressive way of exploring documents. Here we see documents pertaining to human-centric attribute research are projected into the corresponding composition region. We can also allow the user to specify multiple concepts in order to compare documents based on how they're best described by different compositions. Each document's 2D positional constraint is assigned the closest word composition over all specified concepts. So we show here just very basic themes in computer vision. And so by specifying the word reconstruction, we can observe documents mostly projected into the left region of the space. By specifying segmentation, you see that documents are projected into the middle region. And by specifying categorization, we'll see that documents are projected into the right portion of the region. And so the separation of documents into their best composition reflects the distinct research subdisciplines. In particular, segmentation is often used as part of both reconstruction and categorization, hence segmentation papers are positioned in between them. Last, we allow the user to explore documents through analogies. The user can specify the first part of a document is to word analogy, yielding projections where each document is positioned near words that best complete the analogy. In this example, we show the document is the word analogy on top and the resulting projections below. Here, the analogy captures data usage, resulting in segmentation papers that use superpixels as shown in the projection. So as part of the evaluation of our technique, we attended the IEEE Winter Conference on Applications of Computer Vision as an exhibitor in order to demo our working system. We obtained feedback from conference attendees, 21 in total, each averaging about 5 minutes with our system. And so some use some pretty standard concepts in computer vision. So for instance, we show here a user putting in fine-grained classification, resulting in compositions that made sense in general to the attendees. Others use slightly more unconventional phrases, so for instance, transportation or hardware, and yet these still made sense to the attendees, with hardware shown here, yielding compositions near stereo techniques that use calibration, naturally a thing associated with hardware. And yet other attendees wanted to see what papers were used for code and implementation. In this case, one of the attendees was happy to find software packages that he found near deep learning. So in conclusion, we presented a technique to visualize documents through their common usage using citation context to model the usage. The basic idea behind our approach is the use of a joint Word document embedding that provides for interactive document projections through the linear structure of the embeddings. For future work, we'd like to expand our system for more analytics-focused applications. We'd like to incorporate years, authors, and journals into our interface, potentially even representing these in the embedding in the same manner that we're representing documents and words. So we also see our interface as a means for a user to refine embeddings via correcting any potential errors in the document word similarities. We think we can improve on the scalability of our approach. So currently nearest neighbor queries are our overhead, and we think that hashing-based nearest neighbor schemes can bring a modest speed up to this. And last, we'd like to incorporate more traditional document representations, actually using the document text and using things like latent Dirichlet allocation in conjunction with our method in order to have a way of visualizing documents in multiple representations. Thanks.